All right, what we're talking about today is something called the disk method to find what we're going to look for here is the volume of a solid. It's called Solids of Revolution, and I'm hoping you read before you watch the video like I asked you to, because basically what you're going to do is you're going to take a function that you normally would find the area of, you're going to rotate it around either the x or y axis or some line, it could be any vertical or horizontal line, and get a solid. And so I'm going to show you one just so you kind of see what we're talking about here. So this is a function right here. They tell you the function somewhere, but I don't see it on there right now, so we're just going to go with it. What happens is, okay, here's the area that we normally find, and we're going to use integration. Remember, this chapter is applications of integration. So I talked about the other day a little bit how I like to draw this rectangle in here. This rectangle represents one piece of area, and the length of that rectangle is whatever this function is. So if it's x squared, that length is x squared. The width of this rectangle, oh, it says right here, this function is e to the negative x, is what it says. All right, so this length of this would be e to the negative x. The width is what we call delta x. So this is what we're going to do today. You can move the rectangle. You can pick whatever rectangle. When we do them, we just pick a rectangle. I usually put them in the middle, but it doesn't matter. So I'm moving the rectangle. So here's what we're going to do. I'm just going to show you how you go across the x-axis. When you do this, you notice if I go all the way through there, I get a disk. That's why it's called the disk method. Okay? So when I go back to my page that I was on, the disk method, a disk has a volume, and that's what we need to start with. The volume of a disk itself, a disk is a circle, so it's pi r squared, times the width of that disk. If I can go back and forth here, remember what I said the width of the rectangle was? The disk is going to have that same height or width. You can even call it a height if you want, but that is going to be delta x. Okay, so when we go back to my picture right here, remember that what we want is we want to have a whole bunch of those rectangles. So I'm going to go back. I'm going to have a whole bunch of those rectangles, and I want all of the rectangles all the way to infinity to do what this does. And when that happens, I revolve the whole region. And if I revolve the whole region, I get a solid. That's the solid. And a solid has a volume, not an area, so that's why we're finding volume. Let me make that transparent so you can see. So here's this piece right there, and I can move that one trial, I guess you could say, the one that we're looking at, anywhere I want. Okay, so they tell you here's the actual volume of that solid, and we'll try that in class and I'll show you how it gets there. But let me go back to this disk method. Here's the thing, if I go back to our volume formula, it says pi r squared delta x. Well, I want to add up all of the disk, so I'm going to add up all of them, and when I add up all of them, that's where I get an integration. So I'm going to integrate from this point to this point, whatever they happen to be, of pi. Well, pi is a constant. Now r is the length of the rectangle that I originally started with. Okay, let's see if I can get everything back to where it was here. The length of that rectangle is the same as the function. So r in this case is just that function. So r is, I'm going to call the function r of x. It's actually the function. So you have times r of x, that whole function, and we're going to square that whole function, times delta x, which is d of x. Okay? And the disk method is one method. We do look at other ones. What they don't show you there is this one that they show you, I should say, what they do show you is going around the x-axis. Okay, if I revolve something around the y-axis, it looks a little bit different, and I'm sure my picture will be horrible, so I apologize already. But let's say you have some, I don't know, some function like this. Okay, upside down parabola there. If I want to rotate that around the y-axis like this, I have to draw my rectangle horizontally. And instead of having r of x, we would have the integral of a to b of pi And this function is no longer in terms of x, it's going to be r of y squared, that whole function squared, times, now remember this is not delta x anymore, it's delta y, so dy. So depending on which axes you're going around, if you're going around the y-axis, you want to use this one. If you're going around the x-axis, you use the function in terms of x. Kind of makes sense. All right, the actual integration's not hard. Let's just try one. If you have y equals 4 minus x squared, we're going to go about the x. I always graph these first. 1, 2, 3, 4, and I know that's a point. 1, 2, 3, well, it'd be 2, right? And they didn't really tell me anything else. Let's just assume I'm just going from 0 to 2 for this time. If they don't tell you, you just have to figure out where functions would intersect, kind of like what we did the other day. So here's my area. I'm going to go about the x-axis, so that means my rectangle is going to be up and down. Well, you can't really see that, but there's a rectangle in there. The length of my rectangle, so volume equals pi times r. My length would be 4 minus x squared, that whole thing squared, times the width, which is dx. And I integrate that from 0 to 2. I'm just going to move the pi out front because it's a constant. If I integrate that, I probably better FOIL, so that's 16 minus 8x squared plus x to the 4th dx. And from there you can integrate, I'm pretty sure you can, 16x minus 8x cubed over 3 plus x to the 5th over 5, and you would go from 0 to 2. And if you think about that, you can kind of visualize what that shape would look like, what type of shape that would be. Okay? If you go about the y-axis, well, if you go about the y-axis, you do the same thing. But the only difference is, if I wanted this same equation right here to go about the y-axis, so I'm going to use the same one, y equals 4 minus x squared, but I want to go about the y, it's still going to be pi. My boundaries have changed because if I go about the y-axis, my rectangle is horizontal. So my rectangle would go from down here all the way up to here, which in this case, in our problem, that would go from 0 to 4. Now, I need the function in terms of y. So I'd want to, or in terms of x equals, basically, because I want the function in terms of y. So what I would need to do is just solve that. X would equal 4 minus y, the square root of that. 4 minus y, that's your r. So this is r equals that, because from here to here is 4 minus y. And I square that times dy. So pi from 0 to 4 of 4 minus y dy. And then what you do is you integrate in terms of y. So pi 0, oops, I don't want that anymore. Pi, that'd be 4y minus y squared over 2 from 0 to 4, and you plug in your numbers and you get your area. By the way, just leave your area in terms of pi. You don't have to multiply everything by 3.14. It's actually a little annoying, so just don't do it. All right, one thing I want you to make sure you ask me about in class is what if it doesn't go all the way down to like the x or y axis? What do I do then? What if it just goes, stops? Okay, have a great day.